The fastest fighter jet in the world. An unmatched weapons system. Able to fire 6 missiles at 6 separate targets from almost 200 miles away. 30 years after its inception, it is still without peer. Now, the F-14 Tomcat on Modern Marvels. October 7th, 2001. Missiles from lethal American fighter jets rain onto Afghanistan as a response to the terrorist attacks on America. The bombings are devastating. Stealth B-2s, B-52s, and F-16 Falcons are involved. But the majority of the assault is led by one powerful and deadly plane, the F-14 Tomcat.
There's no other airplane before that or since that has the entire range of capabilities, carrying all kinds of weapons, doing dogfights, doing maritime air superiority, combat air defense.
The F-14 is very unique in the sense that it can carry a very high payload. It can fly a long distance. It can fly very fast and very high. And most other airplanes can't do that.
No other fighter jet carries the F-14's unique combination of weapons. The Tomcat's arsenal includes one 20mm cannon, 4 Sidewinder air-to-air missiles, 6 Sparrow air-to-air missiles, 6 1,000-pound Phoenix missiles, and 4 2,000-pound laser-guided bombs.
The ability to cycle between an M61 gun, 20mm cannon, you can go to a Sidewinder air-to-air heat-seeking missile, you can go to a radar Sparrow if you wanted to intermediate range, and you can go with the long-range Phoenix.
Its radar is the most effective of any fighter jet today. Its state-of-the-art system can spot an oncoming enemy plane at almost 200 miles. It can detect targets as low as 50 feet and as high as 80,000 feet, and is 3 times faster than the radar of any other fighter jet. It transmits and receives information through a 36-inch antenna mounted on the nose of the plane. This completely digital system has the ability to track 24 targets and to fire the 6 Phoenix missiles at 6 different targets simultaneously. All of the other world's fighters can only attack one target at a time. The Phoenix can be fired from almost 200 miles away. In fact, because of the F-14's long-distance radar, its adversary would have no idea it was being fired upon.
It also has defensive electronic countermeasures built into the radar. So it's harder for the enemy to detect and to jam against this radar.
By the time his radar would have detected you, he'd be dead.
It remains today really the benchmark of the multi-mission fighter attack airplane. It's high-speed intercept, Mach 2.4. It's capable of air combat maneuvering. Variable sweep wing gives it a dogfight capability second to none.
With its sleek swept-back wings and twin vertical tails, its ahead-of-its-time design is also one of the most recognizable in the world.
Well, the most obvious feature about the F-14 that makes it unique is the variable geometry wings, which allows us to operate over a pretty wide envelope for both high and low-speed maneuvering.
The wings sweep back to reduce drag at supersonic speed and sweep forward to allow takeoff and landing on the deck of an aircraft carrier. The extended wings enable as much air as possible to pass over them, causing lift. At supersonic speeds, the wings tuck back against the body, making it as aerodynamic as possible.
The airplane has an air data computer, and it calculates the Mach number, and the angle of attack is calculated via probes on the side of the airplane that measure air data variables. and the signals are sent to the mechanical actuators, which extend and retract the flaps and sweep the wings back and forth.
The wings start sweeping back in the 0.6 Mach range. At 0.9 Mach, they've reached their maximum angle of 68 degrees.
As the pilot dogfights and as the air combat maneuvering progresses, the wing continues to sweep back and forth as he slows down, as he accelerates.
Powerful GE twin-turbo engines allow the Tomcat to reach speeds of up to 2.4 Mach, or almost 1,800 miles per hour. Despite being one of the older aircrafts in service, the F-14 showed its importance in Afghanistan. During the air war phase of the campaign, the closest naval carrier was still 850 miles from the Afghani border. But with the Tomcat's 2,900-gallon fuel tank, it was able to complete bombing missions without stopping to refuel. That's something the newer F-16 and F-18 couldn't do.
They're smaller airplanes, and they typically have smaller ranges and smaller payloads.
The Lantern, low-altitude navigation and targeting infrared for night pod, allows the F-14 to drop 2,000-pound laser-guided smart bombs on hard-to-find targets. First, its TV camera searches and identifies targets from up to 40,000 feet. Then its targeting pod fires a laser beam.
That can be used to let you ride at some kind of a guided weapon that'll follow that beam.
In addition, it displays real-time video images and passes on GPS coordinates to naval ships or other planes. No other plane has this capacity. Also, the TARPS, Tactical Airborne Reconnaissance Pod System, provides targeting information with clear digital still images from over 600 miles away.
Go in and fly for more than 1,000 miles, go in deep into enemy territory, get pictures, photographs, and take real-time video. They can do that better than anybody.
Since its inception 30 years ago, the F-14 has always been the world's most complete military fighter. It was born out of the Soviet threat in the early 1960s. With the Cold War heating up, the Soviet Union developed a large family of surface-to-surface cruise missiles that flew very low to the Earth. At low altitudes, there were more signals that could interfere with the radar on U.S. ships. It might not be able to pick up these dangerous missiles until they were too close. The Soviets also had deadly air-to-surface bombs. U.S. fighter planes did not have the ability to intercept these missiles.
The Russian attack aircraft that could come in from, hundreds of miles away and do a pretty devastating job at a carrier group if they got too close.
In the early 60s, the Pentagon realized it needed an aircraft that could take on the Soviets.
We needed air superiority, which required an air combat maneuverable fighter aircraft, capable of being nimble and agile and dogfighting.
The Pentagon knew the plane should have a powerful radar system to quickly intercept an enemy missile.
And that was the ability to protect the carrier fleet and to be able to go out hundreds of miles and detect anybody that's incoming from a long range.
In November 1962, the Pentagon gave Grumman Aircraft the contract for this challenging job. It created the F-111, which began flying on May 18, 1965. But the F-111 had several problems. It was a whopping 85,000-pound fighter. It was too big to land on an aircraft carrier, and its swing wings were changed manually by the pilot.
What the Navy really wanted was a fighter aircraft, and the fighter aircraft that the F-111 represented wasn't a particularly good fighter. It was too big, it carried too much fuel.
In 1966, Secretary of Defense Robert McNamara stepped in.
We do not yet have any effective operative defense against ballistic missiles.
He stressed the requirements for the new fighter: Mach 2 speed with great maneuverability, a powerful radar system, the ability to carry a variety of weapons. Furthermore, the new plane had to be light enough to take off from and land on an aircraft carrier. During the summer of 1968, the DoD solicited engineering proposals for the new fighter from 5 leading aerospace contractors. In January 1969, Grumman again was declared the winner. At $5 billion, this was the largest military contract in history. But the contract was a demanding one. Grumman was bound to deliver 700 airplanes over 8 years. And an even more daunting requirement for Grumman engineers. They would have to have a plane ready for a test flight in 17 months, half the usual time for a program of this type.
From contract signature to the delivery of the airplane, we had a requirement of 51 months.
Work on the plane began in August of 1969. A first decision was to retain a feature from the lumbering F-111, its AUG-9 Doppler radar system. This was a significant improvement over pulse radar from World War II, which was still being used on aircraft carriers in the 1960s. Pulse radar measures distances from targets. It works fine out in the open sea, but it becomes cluttered closer to land, near mountains, for example, where there are many other signals. Doppler radar only measures moving targets without regard to background. It could easily pick up the deadly cruise missile. While the F-111 had only 2 forms of pulse radar and 2 forms of Doppler, the new plane would have 6 types of radar operation, 4 in Doppler and 2 in pulse mode. This increased the number of targets the jet could track from 12 to 24. Now the fighter jet had the potential to counter the cruise missile further out. With a proper air-to-air weapon, the jet could theoretically down the Soviet missiles.
The AUG-9, as designed and developed for the F-111, was an excellent transfer to the F-14. We needed it for the excellent range it has and for its excellent capability.
Grumman engineers then turned their attention to designing the new fighter. But to bring it to reality, they would have to reinvent the basic components of the military aircraft. In 1969, after landing the $5 billion contract for the F-14, the new generation of fighter plane, Grumman set its sights on the design. Engineers faced the sobering challenge of how to design a jet plane that could travel at Mach 2 speeds, maneuver quickly in battle, yet still carry thousands of pounds of weapons. Their first priority was the swing wing. The concept is simple. A swing wing lets the plane go faster by swinging resistance out of the way. Grumman had developed the first swing wing plane to fly, the XF-10, in May of 1952. But it was an aircraft with a host of engine stability and control problems. The XF-10 program was scrapped the next year. But the swing wing concept had shown promise.
We learned an awful lot in the process of doing it. And after that, we were teamed with General Dynamics in the production of the F-111 aircraft. There was another case where Grumman got very valuable experience in dealing with variable sweep wings. So we pretty well had a grip on what not to do when the F-14 program came along.
But not at first. Some of Kress's colleagues felt the wings of the F-14 should be swept back at Mach 1.2, or 900 miles per hour.
When the fellows came in and dumped that number on me, I was quite shocked. And I started to ask, what would anybody be doing at Mach 1.2? With the wings unswept, the airplane would be screaming at them.
In aircraft before the F-14, a pilot was responsible for sweeping the wings back. Kress felt a system was needed to control the dynamics of the plane and free up the pilots from worrying about the swing wing's optimum position. Kress's team devised an air data computer called the Mach Sweep Programmer. It would automatically swing the wings. There would no longer be the need for any action by the pilot. One of several innovations from Kress.
That's probably the most unique characteristic of the airplane in the sense that it provided the first truly computer-controlled operation variable swept-wing aircraft. The pilot could override the computer if there was a computer failure.
Kress's team put the wings through countless wind tunnel trials.
What we did as the Mach number increased beyond Mach 0.7, we gradually started to sweep the wings back until they were at full sweep at about Mach 0.95. There was tremendous compatibility between limitation of bending moments and making the airplane a superb fighter in terms of drag and buffet and turning performance.
Since it would carry thousands of pounds of weapons, Grumman chose titanium for their swing wing instead of steel. Titanium is stronger and lighter than steel, but a difficult metal to work with. It is hard to bend or weld. Furthermore, many aeronautical engineers were skeptical of welding. However, Grumman developed a welding process called electron beam welding. This method fuses two pieces of titanium together.
It consists of bringing the two surfaces to be welded into close proximity and passing a very intense electron beam down the little crack which remains, which melts the metal all the way through the depths of the crack.
Several pieces of titanium were welded together to form the wing box.
The wing box structure is the structure that effectively went from one side of the aircraft on its wing pivot to the other side of the aircraft on that side's wing pivot.
The titanium box beam was a marvelous piece of engineering. It weighs 2,500 pounds, and it's all welded together. It holds the whole airplane together.
Once in place, the fuselage was subjected to over 500 test drops.
They've actually had some crashes where the F-14 has gone into mud or water or whatever, and the wings are ripped off. Most of the body is pretty well destroyed, but the titanium center fuselage is intact and almost undisturbed.
The F-14 would be made up of 35% titanium, with the wing box composed entirely of titanium. The rest of the F-14 would consist of approximately 40% aluminum alloy, less than 1% boron, and about 18% steel. The titanium would make for a much lighter plane, 40,000 pounds less than the F-111. Of great importance in jet performance is the thrust-to-weight ratio. Aircraft thrust provided by the jet engines in pounds, divided by the aircraft weight in pounds. The greater the ratio, the better the performance. In order to achieve the ideal thrust-to-weight ratio, Grumman engineers began an exhaustive test process, with most of the emphasis on the swing wing. They subjected models with more than 2,000 configurations to over 9,000 hours of wind tunnel testing. By January 1968, they had found their ideal model, number 303E, a swing wing powered by twin jet engines, each producing 20,000 pounds of thrust.
The twin engines were significantly separated from one another. And early on, we didn't really realize how valuable that separation would become as a place where we could nest missiles, one behind the other. Missiles as big as the Phoenix missile and as big as 2,000-pound bombs.
The cumbersome F-111 had an internal bomb bay and permanent fittings for carrying the 6 Phoenix missiles. The Tomcat would carry its weapons externally. The result? The F-14 would not carry the extra dead weight of bomb or missile fittings.
Which was an innovation that was developed here at Grumman. And it's what we call the pallet concept. And if you look at the bottom of the F-14 airplane, you'll see the 2 Phoenix missiles, or 2 2,000-pound bombs. They're located on rails, and the rails are contoured such that the fins of the missiles and part of the missile is covered by the rails, which cuts the aerodynamic drag of the weapons.
Depending on the mission, the pallets could be changed very quickly to load up different weapons. F-14 designers took another chance, the twin vertical tails. This configuration had never been used before in any jet fighter. 2 shorter tails as opposed to a single taller tail is an advantage where there is a height limit on the carrier hangar deck. But most importantly, the 2 tails create greater stability.
When you have 2 tails, you have twice as much surface that can be applied to the aerodynamic forces. You can get twice as much correction factors. You want something that straightens the airplane out. If you lose an engine, it tends to slide laterally and rotate, and you want it to stop rotating.
Another revolutionary design feature came from Kress. The crew of two, the pilot and the RIO, radar interception officer, would be seated in tandem. This would reduce drag on the aircraft, as it would make for a thinner cockpit. Target date for the test flight of the first of 12 prototypes was January 1971. The company planned to get its first bird in the air a month ahead of schedule. With many modern innovations in place on the F-14 design, confidence was running high. However, the road to production would be paved with crashes and loss of life. The first of what would be thousands of test flights for the new F-14 was planned for December 21st, 1970, a month ahead of schedule. Robert Smythe and Bill Miller would be co-pilots. As darkness fell, the F-14 prototype made 2 wide circles around the airfield. It was a simple but successful 10-minute flight. The swing wings weren't used. Despite the short flight, Grumman was optimistic about its second flight. That would come only 9 days later, on December 30th. The plane would attempt to go supersonic and sweep the wings for the first time. Smythe and Miller would be in the cockpit again. Dennis Romano would be in the chase airplane for the flight.
There was a lot of hoopla, and there were a lot of people there. And it was out at our Calverton facility out on the eastern end of Long Island. The F-14 got airborne and flew out off the south shore of Long Island. There was a good stiff breeze blowing, probably about 25 knots.
The flight began smoothly, but well away from the base at 10,000 feet, the F-14 started leaking hydraulic fluid. The leak was caused by a resonance or rhythmic shaking in the system, produced by pulsations from the hydraulic pumps. That led to a break in the hydraulic lines. The pilots had to bring the plane back.
We lost the hydraulic power for the controls, so we tried to get it to field, and he almost got back, and all of a sudden the airplane started to fishtail, and they just speared in this plume of smoke because they were going down with the airplane. And I felt I had lost 2 friends.
I saw the backseat guy, Bob Smythe, and the front seat guy, Bill Miller, come out. They ejected. I saw Bob Smythe's parachute descending into the exploding fireball. Heat from the rising fireball lifted him up, and the wind blew him after the wreckage. And the bottom of his flight suit was singed from the heat. But they both escaped. The aircraft, unfortunately, was completely lost.
And all it took was to go ahead and change some of the clamping on the hydraulic, and the problem went away.
5 months later, the same test pilots, Miller and Smythe, successfully reached supersonic speed and utilized the swing wings for the first time.
130 degrees, over.
Trials continued at Calverton and Long Island. 600 separate tests were conducted with each flight. Information from sensors was telemetered back to engineers at a computer console. They would examine the data, then clear pilots for the next test flight.
Let's say out on the wing panel, you had 50 stress points on the wing that you wanted to measure. Each wing you put 50 instrumentation points. And these are little sensors, and each one of those is a parameter. 600 of those are being recorded constantly. Some of them are electrical, some of them are stress, structure, engine, fuel system. And what you happen to be testing primarily that day is where the focus and the emphasis is. We could go out and continue to do our testing until the engineer on his flight test console would see some sort of a danger point.
Flight 4, when ready, is over. Roger. Yes, 3 confirms Montana.
And decide at least we would stop that portion of the test, but then go on to some others.
The structural test program was the most demanding part of the testing, for both plane and pilot. The F-14 flew every maneuver imaginable at low speeds, high speeds, and at all altitudes.
Sometimes, depending upon the flight configuration and the loading of the airplane, we would roll the airplane as high as 270 degrees per second. And for an airplane that weighed 40,000 pounds, that was pretty good. A lot of inertia. We did that at twice the speed of sound. Then we also did it at 900 miles an hour, 5,000 feet.
Up to 135 structural tests would be performed in a 4-hour flight.
And I will tell you that even for a young man at the end of a 4.5-hour structural flight, you were pretty worn out.
Disaster struck in June 1971 when Bill Miller, the pilot from the first flights, mysteriously lost control of his plane, resulting in his death. But testing continued. The biggest problem in the early test flights was the engine. The TF-30 Pratt & Whitney engine had been designed for the F-111. Because of a contractual obligation with Pratt & Whitney, Grumman would use the TF-30 on its early F-14s. The engines weren't built to withstand the aerodynamic stresses of the Tomcat.
Every time you fly, you're stretching the envelope. You're not just flying straight and level like a regular jet passenger airplane. You're flying very fast. You're stressing it aerodynamically, inertially, every which way.
Sometimes fan blades would break off and fly through the rest of the engine, destroying it entirely.
They're large. They have quite a bit of mass associated with them, and they spin at a very high RPM.
Engineers soon solved that problem when they developed a new and improved engine intended to prevent turbine blade cracking. Fan blades were made from stronger titanium alloy, and steel casings were employed around the fan belts as a containment precaution. If a fan blade did disintegrate, nothing would come through to harm the engine. Only 2 more planes were lost over the next 18 months. The testing was going extraordinarily well.
Structurally, the plane was incredible.
But the most important and intricate testing was still ahead. This would involve firing 6 Phoenix missiles at 6 separate targets.
You have to have 6 separate drones flying in 6 different places. And you have to have an F-14 with 6 Phoenix missiles. And you have to have all the range and all the coordination capability. A big deal.
The first trial would take place at the Naval Missile Test Center at Point Mugu, California, in November 1972. Missiles would be fired at targets flying from sea level to 100,000 feet. It would be a pioneering effort.
Nobody has ever attempted to fire at 6 widely separated targets simultaneously.
Fox 1, 1's away, 2's in the air, 6 in the air.
Only 1 of the 6 missiles failed to hit its target.
5 directly, smashed right into them. It's incredible. And the one that missed, I don't recall exactly if it was within lethal range, but it wasn't far off.
The Pentagon was sold. 3 months after the 6-on-6 test, Grumman delivered 234 F-14s to the Navy. The F-14 Tomcat program hit stride. Over the next 3 decades, thanks to continuing improvements, the Tomcat would repeatedly prove its worth in combat action. However, in 1979, an attempt to help an American ally almost resulted in disaster for the Tomcat and the United States. After its delivery to the U.S. Naval Fleet in early 1973, the F-14 quickly became one of the most feared and respected fighters in the sky. But during the same year, continuing Soviet aggressions prompted an unusual decision involving the Tomcat that would put the U.S. in a very vulnerable position. Iran, America's ally at the time, was concerned about the Soviet MiG-25s that were flying over its country at 50,000 feet. MiGs were able to fly at speeds exceeding Mach 2. The Shah of Iran asked President Nixon for assistance in intercepting the high-speed intruders. Nixon told the Shah he could order either the F-14 Tomcat from the U.S. Navy or the F-15 Eagle from the Air Force.
The only airplane that was really capable of taking down the MiG-25 was the F-14 with the Phoenix missile on the Phoenix missile system. The F-15 was appealing to the Shah because it was an Air Force aircraft, and there were a substantial Air Force presence in Iran.
The Shah asked to make his decision from a fly-off or air show between the two. Nixon agreed. The fly-off would take place on a warm August day in 1973. The F-15 flew first. Then the Tomcat took to the air with Dennis Romano as co-pilot.
90-degree turn to the right, a 270-degree turn back to the runway heading, flew down the runway at 500 feet in a 90-degree bank, and swept the wings forward from 68 degrees to 20 degrees while we were doing that maneuver. We touched the airplane down and then pulled the airplane up into a vertical climb, left the gear and flaps down, rolled the airplane directly over the end of the runway, which was very impressive.
The Shah chose the Tomcat. In January of 1976, the Navy delivered 79 F-14s to Iran. With the exception of a few classified avionics items, the Iranian Tomcat was identical to the U.S. Navy version. Grumman technicians and U.S. Navy pilots provided the technical and training support. However, in early 1979, increasing unrest in Iran led to the overthrow of the Shah. He was replaced by the radical Islamic fundamentalist government of Ayatollah Khomeini. 79 of the best fighter jets in the world were now in the hands of an American enemy. But by August, every Tomcat had mysteriously been sabotaged, so they could no longer fire their missiles. Even today, no one but the saboteurs know who was responsible, but some suspect departing Grumman technicians.
The rumor that I heard was that they took some of the electronics as they were leaving. I do not know whether that's a fact or not.
What is known is this. With an arms embargo imposed against Iran by the U.S., a severe parts and maintenance problem occurred. This made the Iranian Tomcats virtually useless.
There are very detailed inspections and parts that have to be replaced on a regular basis. And if you don't maintain it, in a couple of months, it'll just go into complete disrepair. And I think that's what really happened. The real knowledge base was the group of technicians that had gone to support the F-14. Once they lost the parts and once they lost the expertise, just a matter of time.
As far as we know, the airplanes are essentially sitting in desert storage with very little usage and no spare parts.
2 years later, in 1981, the Tomcat exhibited its prowess. When the USS Nimitz entered the Gulf of Sidra in the southern Mediterranean to carry out routine training, Libya claimed the Gulf as its own territorial waters. Flying Soviet Su-22s, Libyan pilots fired at the Tomcats. Using sidewinders, the Tomcats shot down both Soviet jets. 8 years later, Libyan pilots again confronted the F-14. This time, they were flying the mighty and very fast Soviet MiG jets.
Second engagement, we actually tried 4 or 5 different maneuvers to avoid the airplanes that were oncoming. And each time we made a turn, they turned into us, which meant that it was a confrontation.
He's jinked back into me for the 4th time, and pops one again. One. Roger that. I got the other one. Good kill, good kill. Hey, good kill.
But once again, 2 Tomcat pilots shot down 2 Libyan fighters. It was a relatively easy fight for the Tomcat pilots.
That was actually almost Sidewinder 101. They've never really been challenged, and they'd like to be.
Despite its superior ability, aeronautical experts felt that by the end of the 1980s, the Tomcat would eventually be phased out by some of the newer fighter jets, like the F-16 Falcon and the F-18 Hornet. But improvements over that decade and the 1990s would keep the F-14 on a par with any other plane in the world. One of the most important upgrades involved the F-14's engine. The primary concern with the F-14 during its first 10 years was compressor stalls in the engine. The earlier engines were ideal for supersonic speed, but not for extreme combat maneuvering.
The airplane was a fighter, and as a fighter, there are a tremendous number of rapid throttle excursions.
You had to watch carefully to make sure you didn't get it too high angle of an attack, get too slow or whatever, get outside the allowable envelope.
Irregular airflow would cause the engine to stall. The stalls occurred at high altitudes and low speeds. If not corrected immediately, the aircraft would begin to swerve and go into an uncontrollable spin. Because of this, some 19 F-14s were lost. The newer GE engines installed in 1984 allowed pilots to fly their Tomcats through extreme angles of attack and maneuver without worrying about compressor stalls.
The GE F-110 engine really provided the thrust and the performance to the airplane that it had been originally designed for. The GE engine increased the afterburning thrust, the total thrust in the airplane, from about 21,000 to over 28,000. This is about a 40% increase in thrust. It also provided a computer fuel control, which gave us stall-free operation throughout the envelope.
In the early 90s came the addition of better radar and avionics. The digital radar system introduced in 1990 gave the Tomcat its unparalleled ability to track targets at nearly 200 miles from almost any altitude.
The APG radar kind of brought it from an Oldsmobile to a Ferrari, so to speak, in avionics.
Today's new infrared search and track system, installed in 1990, allows an F-14 pilot to see an enemy from a heat source up to 300 miles away. The Lantern Pod, providing the F-14 with laser-guided weapons, was added in 1995. In 1996, the Tomcat started utilizing this technology when they dropped the laser-guided smart bombs over targets in Bosnia. This earned them the nickname Bombcats. The original F-14 had only 3 computer processors. The newest version has 33.
So you always had your main central computer. Now you have distributed processors all over the airplane doing all kinds of calculations.
That even includes a digital flight control system that prevents the airplane from going into a spin. All of these upgrades would prove beneficial in America's new war. In 2001, F-14 pilots were sometimes flying 2 missions a day over Afghanistan. But the F-14s are only as good as their pilots, and the pilots who fly these Tomcats are arguably the best in the world. They become F-14 pilots only by surviving one of the most demanding training programs in the military, the Top Gun program. It isn't easy becoming an F-14 pilot. Qualifications are rigid. The training is extensive. Since 1972, the program has been called Top Gun. A maximum of only 40 pilots is chosen each year from the thousands of candidates. A pilot must have a minimum of 3 years' experience, flying either the F-18 or F-16. Every aspect of the pilot's experience is taken into consideration. This includes his or her air combat record.
They would see how you did in a dogfight, how you did in air combat maneuvering. I mean, you built a reputation in an airwing.
The pilot's reaction time and ability to handle the plane in a fast-moving situation are evaluated. Candidates must have mastered a variety of fighter maneuvers to qualify for Top Gun. For example, flying 550 miles per hour at 10,000 feet, the pilot needs to have consistently demonstrated the ability to turn a fighter 90 degrees in about 4 seconds.
Tactical ability and air sense, aviation skills, that's entirely what it's based on. I mean, that's where the rubber meets the road, is how well you do flying the airplane.
A pilot must also be in the top 1% of the Navy's annual fitness report. The training is an exhaustive 10-week course. It involves 500 hours of flight time, with 100 hours of combat engagements. In the classroom, would-be Tomcat pilots must demonstrate a detailed understanding of every enemy plane. The Top Gun candidate should be able to identify every missile of a Soviet MiG fighter, how fast the MiG can fly, and even how fast it turns. At a training base in Fallon, Nevada, prospective Top Gun pilots launch a variety of air-to-surface missiles at different targets. They are graded on how close they come to the center of each target.
They have simulated truck convoys, simulated airfields, because the idea is to try to put an airfield out of operation, much like we did in Kabul and things like that, where you try to drop a stick you can't across the runway to cut it so it's no longer usable to the enemy.
The climax of the training is Alpha Strike, in which the students engage their instructors in simulated battles. The instructors will attack F-14 formations, testing the candidates' ability to shoot down enemy interceptors. The instructors fly F-16s, F-18s, and more recently, Soviet MiG fighters.
Your primary target mission is to destroy your air-to-ground target and do that while avoiding enemy fighters. If they're in between you and the target area, then you're going to have to destroy the enemy fighters.
You could end up with a sweep going through of 20, 30 good guys versus 20, 30 bad guys. You end up with 40, 60 airplanes in this one piece of sky. Fights on, you know. That's part of the graduation exercise.
On the ground, commanding officers watch the battles play out on a computer screen. Every move by the Tomcat candidate is recorded on video. Ability to intercept, understanding of weapons, firing capability, even language are reviewed.
The primary thing you're graded on is mission success. Did you make it to the target area and to deliver your weapons on target? From that point on, they get a little more detailed into everything from your time on target to the second. Generally, if you're plus or minus a couple seconds, you're doing pretty good. If you're, 30 seconds off, that's fairly significant.
In addition, the candidates must also endure the SEERS training. SEERS stands for Survival, Evasion, Escape, and Resistance School. Prospective pilots spend 5 days in the mountains or on the beach with very little supplies and no food. In the process, they must also try to avoid being captured.
You're put in a fairly hostile environment. You're given very little in the way of supplies, and you pretty much have to fend for yourself for a few days.
It's real survival.
At the beginning of the 21st century, the survival of the F-14 itself is in question. The rumor is that it will gradually be phased out by 2007 by a new generation of fighters, like the F-35 Joint Strike Fighter. But over 10 years ago, insiders also predicted the demise of the Tomcat.
There was some talk of it not lasting to the end of the century or not being around to start the new century. But with each new upgrade, they put more life and capability into the airplane.
Even the airplanes we currently have could be around for another 25 years.
The world's greatest fighter jet might be too valuable of an asset to retire. The Tomcat may prove its skeptics wrong once again.
To let it fade away and be replaced by anything less capable or more expensive is a big mistake.
The airplane's been around for a long time. It's probably going to be around for several more years. I think every time when who you're going to call, you go to the F-14.